and in this presentation we're going to discuss the SAFE system, also known as the Safe System Approach to Road Safety, which is the underlying principle of the National Road Safety Strategy here in Australia. After watching this presentation, you will be able to describe the Safe System Approach to Road Safety, discuss the SAFE system in the broader context of the road design system, and understand how the four components of the SAFE system influence road design. In conjunction with this topic, there are a few recommended readings. First of all, I would suggest that you have a look at the Austroads Guide to Road Design. For those of you who are not familiar with Austroads, they're the peak organisation of Australasian road transport and traffic agencies. Both the Austroads Guide for Road Design and Pavement Design have been uploaded to the Moodle website and will form valuable resources when you're conducting both the major road design assignment and the pavement design assignment. In particular, Part 3 of the Austroads Guide to Road Design covers geometric design, and we'll come back and look at this in week 4 of this unit. For this week, it'd be worthwhile looking at Part 1 of the Austroads Guide to Road Design, in particular Section 2.3, which provides the Austroads interpretation of the SAFE system. Another useful resource is the Traffic Engineering and Management textbook that is produced by the Department of Civil Engineering here at Monash and was edited by Dr. Alexa Del Bosque and Professor Bill Young. This book is not a required text for this subject, but it does have lots of useful information, and I'd strongly recommend you get a copy if you're considering a career in traffic engineering, transport planning, or road design. Finally, you may be interested in looking at the National Road Safety Strategy. I've uploaded a copy of this document onto the Moodle website. So, looking back at the previous presentation, we introduced the Road Traffic Design System, which forms a framework for the material that will be covered throughout this unit. While much of the work will focus on the design process and the design elements, we begin this unit by looking at the road context. As mentioned in the previous presentation, both the road traffic system and the design process exist within a wider context that's affected by political considerations, the institutional structure of the road authority, and the planning process. This provides both constraints and opportunities on what can be achieved within our road traffic system. When we discuss road safety, and in particular the SAFE system, we're considering political, institutional, and planning factors that influence the way we design and operate our road network. So, why is road safety such an important issue? Well, I mentioned some of these statistics in the previous presentation, but globally it's estimated that about 1.27 million people die on the world's roads every year, and up to 50 million people suffer serious injury that requires some form of hospital treatment. In Australia, our roads are relatively safe compared to other nations. In fact, most of the burden of injury, roughly 90%, from road traffic crashes occurs in low and middle income countries, despite these countries only representing about half of the number of vehicles in the world. Globally, this burden of injury that's associated with road traffic crashes results in enormous economic, social, community, and individual costs. These are estimated at over $500 billion annually through loss of life, disability-adjusted life years, and damage to property. When we consider Australia, for example, in 2017, there were 1,227 people who lost their lives on Australian roads, and over 10,000 people suffered a serious injury as a result of being involved in a collision. And road traffic injuries disproportionately impact children, young adults and older adults, and they're the number one cause of death for people aged between 15 and 29 years of age. This slide was included in the previous presentation and gives an example of how Australia's road toll compares internationally. From the graph, we can see that while we have a relatively safe road network, we are by no means the safest country in the world when it comes to road safety, and this implies that there are things that can continue to be done to help reduce the road toll and burden associated with injury. This slide was included in the previous presentation and gives an example of how Australia's road toll compares internationally. From the graph, we can see that while we have relatively safe roads here in Australia, we are by no means the safest country in the world when it comes to road safety, and there are things that can continue to be done to help reduce the road toll and the burden associated with this injury. So, how do we go about reducing the road toll in Australia? Well, as I mentioned earlier in this presentation, and as a recommended reading for this week, Australia has adopted a national road safety strategy that's currently under review because it ends in 2020. This strategy was designed to help guide road development and operation throughout the nation. The overarching goal of the strategy is that no person should be killed or seriously injured on Australia's roads. While this is a very ambitious target, there is some recognition that reducing the road toll to zero is not necessarily practical, as some people, unfortunately, will not engage with the road system in a safe manner, whether that be speeding, drink driving, or driving distracted by using their mobile phones, for example. In recognition of this, the strategy sets a target to reduce the annual number of road traffic fatalities by at least 30% and reduce serious injuries, those requiring hospitalisation, by 30%, with the recognition that provided road users are behaving in accordance with the road rules, the road system should be designed so that no collisions result in fatal injury outcomes. In order to achieve these reductions, the National Road Safety Strategy has adopted the Safe System Framework for road safety as the guiding framework. So, what is the Safe System approach? The Safe System approach to road safety is founded on a strong ethical platform that acknowledges the limitations and vulnerabilities of humans in the road traffic system. The guiding principles of the Safe System approach have been formulated by combining the best elements from road safety philosophies of Sweden, where they use a system called Vision Zero, and the Netherlands, who developed a system called Sustainable Safety. And these are currently world leaders in road safety performance. The Safe System requires a holistic view of the transport system and the interactions amongst road users, the road and roadside environment, vehicles, and vehicle speeds. It's inclusive of all road user groups, so vehicle drivers, motorcyclists, pedestrians, cyclists, and heavy vehicles. And the approach recognises that people will make mistakes when operating within the road environment, and that although those mistakes will inevitably lead to road crashes, the road system should be designed to be forgiving and not result in road users being killed or seriously injured. In essence, the Safe System aims to eliminate fatal crashes and significantly reduce serious injury crashes. And to achieve this, the safety interventions identified within the Safe System framework are based on the best available scientific evidence of what is effective. Furthermore, the Safe System recognises that there's a shared responsibility to achieving a safe road system. Road users are responsible for complying with the system rules, and us as system designers and civil engineers need to make sure that we design and operate the road traffic system responsibly. One of the most important principles of the Safe System is that when a road traffic crash does occur, the energies involved in that crash need to reduce to levels that minimize the probability of death and serious injury. So we need to make sure we're providing a safe, crash-worthy system that is forgiving of human error and accommodates the vulnerabilities to serious injury. There's recognition that all aspects of the transport system need to work together, and we need to manage the road infrastructure, speeds, vehicles and road users and their interactions in order to achieve safe mobility. The Safe System approach aims to create a forgiving road system based on 4 key ideals. First, people make mistakes, and we need to recognise that some crashes are inevitable. In essence, there are limits to human performance, and the Safe System guiding philosophy acknowledges that accommodating the limits of human behaviour and judgment is essential, and it recognises that providing users act responsibly, the system should accommodate the fallibility of humans. Next, we need to recognise that people are vulnerable. Our bodies have a limited ability to withstand crash forces without being seriously injured or killed. So there are limits of human tolerance to violent forces, and the Safe System seeks to create a road transport system where collisions only occur within the biomechanical limits of the humans involved. And by doing this, we increase people's chances of surviving in the event of a crash. Next, the Safe System recognises that there's a shared responsibility. So the Safe System approach aims to distribute the responsibility for safety performance of the road transport system with both the system designers and operators. That being said, the system designers and operators depend on compliance by road users in order to achieve a truly safe system, while conversely, individuals who are complying with the road traffic system depend on there being inherently safe design standards and operation for their safety. Finally, we need to acknowledge that we need to strengthen all parts of the system, so the roads and roadsides, make sure people are compliant with speeds, they're using safe vehicles, and road user behaviour is safe. And even if one part of this system fails, we hope that the other parts will still protect the people involved. A simplified way of thinking about road crashes is through the Swiss cheese model of collision and injury causation. This model was developed by Reason, and it uses a systems approach that acknowledges that there are many components of the system that contain barriers and safeguards to prevent an injurious event. As such, an injurious event occurs when there are failures at multiple points within a system. And Reason simplified this theory into a diagrammatic representation where the system is considered as a stack of slices of Swiss cheese. Looking at the slices of Swiss cheese, the slices represent barriers, while the holes in the cheese represent opportunities for failure in the system. An error may allow a problem to pass through one hole or one layer. However, provided the holes in the next layer are in a different place, the problem is avoided. As such, a catastrophic error can only occur if the holes align in every layer. If this happens, this represents an inherently flawed system where a problem at the beginning progresses through to an adverse outcome. Within this model, there are primarily 2 methods for reducing the risk of an incident. Firstly, more barriers can be put in place, requiring the hazard to pass through a greater number of layers. Layers can also be made more robust, in essence, reducing the number and size of holes, making it more likely to stop errors before they occur. So, if we think about a crash that occurs on a country road in wet conditions, where the driver is driving at an unsafe speed, with a poorly maintained vehicle and is fatigued or distracted while driving, we can see that there are multiple failures in the system across the four components of the road, vehicle, vehicle speed, and road users. And in this situation, it might not be a surprise that enough factors have aligned for a crash to occur. The Swiss cheese model essentially states that the risk of that crash occurring would reduce as we resolve some of these road safety issues, or we reduce the number of holes in the preventative layers. And that brings us to the components of the SAFE system, being safe roads and roadsides, safe speeds, safe road users, and safe vehicles. Through controlling these factors, we aim to manage the human tolerance to crash forces, and we complement these factors through an understanding of crashes and their risks, innovation, legislation and enforcement, leadership and capability, education and information, and admission to the system. So looking at those four key components in more detail, so for safe roads, we need to make sure that these are predictable and forgiving of mistakes. They're self-explaining in that their design encourages safe travel speeds. For safe speeds, we want to encourage travel speeds that suit the function and level of safety of the road. And we want to make sure that people understand and comply with the speed limits and drive to the conditions. We want to make sure that people are selecting safe vehicles that can help to prevent crashes and protect road users, including pedestrians and cyclists, in the event of a crash. And we need to make sure that our road users are adopting safe road use. So our road users are skilled and competent, alert and unimpaired. They comply with the road rules and take steps to improve safety, and they also demand and expect safety improvements throughout the road network. Another really important factor within the SAFE system is recognition that we cannot design a road system for only motor vehicle occupants, and that a truly safe system cannot ignore the vulnerability of some road user groups, which in itself can be a major determinant of injury outcome. So in order to design a truly safe system, we need to make sure we're protecting our most vulnerable road users, so our pedestrians, cyclists, motorcyclists, children, and the elderly. And increasingly, now we need to consider new forms of mobility, such as micromobility devices like electric scooters. Within the National Road Safety Strategy, across the four key elements of the SAFE system, key crash types and road safety issues have been identified throughout Australia, and then initiatives have been developed in line with safe system thinking on how to deal with these crash types. For example, if we consider run-off road crashes, the strategy identifies that safe roads, through the provision of infrastructure such as wire rope barriers and vehicles travelling at safe speeds so that they can recover in time, are two methods for addressing that issue. Safer vehicles that incorporate systems such as lane keeping technology would also be an initiative that could be implemented to address this particular road safety issue. In the following slides, we're going to discuss each component of the SAFE system in a little bit more detail, starting with a look at speed. One of the most fundamental determinants of both the risk of injury in a collision and your chance of being involved in a collision is vehicle speed. The diagram on this slide shows how the risk of injury increases as vehicle speed increases over 60 kilometers per hour in a 60 kilometer per hour speed zone. And this is based on some research that was conducted in South Australia in the 1990s by Cloden. In essence, Cloden's research found that if you're 5 kilometres over the speed limit, you double your chances of being in a serious collision. At 10 kilometres over the speed limit, you're you're 4 times more likely, while at 20 kilometers over the speed limit, your risk of being in a serious collision is 32 times greater. As engineers, I'm sure you can all appreciate that crashes and the injuries sustained are largely dictated by the laws of physics, in particular the kinetic energy which needs to be dissipated when a collision occurs. I'm sure you can all remember kinetic energy can be calculated as half the mass of an object multiplied by the square of its velocity. Based on this simple equation, we can appreciate how, at higher travel speeds, there's a greater amount of kinetic energy involved in a collision. On Moodle, I've uploaded a video that was produced by the Transport Accident Commission a few years ago and was based on some research that was conducted here at Monash. The video shows how even a small change in speed can have a significant impact on the stopping distance of vehicles. Vehicle speed is also a crucial safety issue for vulnerable road users, as speed is a powerful determinant of crash risk. For pedestrians and cyclists, they're only really safe when vehicle speeds are low, in the order of 30 to 40 kilometers per hour. Most OECD countries have adopted general urban speed limits of 50 kilometers per hour. However, there's been quite a push in recent times to adopt a 30 kilometer per hour speed limit, particularly in highly pedestrianised areas. The diagram on this slide is similar to the previous slide, but it shows the risk of death for pedestrians, and we can see that for all pedestrians over 40 km per hour impact speeds, the risk significantly increases, but for more vulnerable pedestrian groups, such as older pedestrians, this increase occurs at even lower speeds. Historically, when we discuss road design, there's always been an emphasis on increasing mobility. This can be considered the movement function in our functional classification of roads, or the need for efficiency when we think about safety, efficiency, and amenity. In essence, historically, we've strived for the highest mobility possible until safety was compromised too much. But as we discussed in the previous presentation, there are trade-offs between safety, efficiency, and amenity. Still, many of the current speed limits that we use on our roads are in favour of higher mobility, often at the expense of safety. So in essence, we're making a trade-off where we sacrifice safety to an extent to improve the efficiency of the road system. In Australia, often our urban speed limits are about 10 kilometres per hour higher than in other Western countries. However, in line with safe system thinking, speeds should be at a level that do not exceed human tolerance to violent forces. So clearly, while we have a national strategy for road safety, we do not necessarily have complete compliance, reflecting the trade-off that is made in our road design system. Of course, speed is not a simple variable, and there are various factors that influence the speed that drivers choose, including driver factors, road and traffic conditions, the speed zone they're in, crash and injury risk, police enforcement, education, and vehicle factors. Of course, arguably, the thing that has the greatest influence on drivers' choice of speed is the speed limit that they're in. And research has demonstrated that crash severity declines whenever speed limits are reduced. For example, in Victoria, after default urban speed limits of 50 kilometres per hour were introduced, pedestrian casualty crashes fell by 20%, and serious crashes involving pedestrians dropped by 45%. Similarly, when the speed limits were reduced from 110 to 100 kilometres per hour on urban freeways, there was a 19% drop in the casualty crash rate on freeways. Looking at the next factor in our safe system, the road user, driver and rider factors really do play an important part in the system, and the system relies on road users to behave in accordance with the rules. Notwithstanding, there's recognition that drivers and riders are human and therefore make errors. They consistently tend to overestimate what's a safe speed. They can be influenced by perceptions about risk or being caught. They're concerned more about a crash than the injury risk. They can be encouraged to drive faster based on the travel speed of those around them, so there's a contagious effect. And there's variations in the skills and abilities of our drivers. In particular, young drivers tend to have the lowest level of skill, but tend to choose to travel the fastest. And we'll discuss these issues in more detail in week 3 when we talk about human factors. One of the key ways that we in Australia and in many other nations in the world try to improve road user behaviour is through a licensing system. A licensing system establishes an access or entry level of ability and skill, and it creates a minimum level of competency that we expect our drivers to have in order to access the system. Even the best vehicles can't protect occupants in many common crash types. As I've said before, safe impact speeds generally fall below 30 to 50 kilometres per hour, and this really depends on the type of crash. And in general, it's assumed that drivers do tend to overestimate the protective capabilities of their vehicles. Looking at some of our common crash types, so the threshold for injury really does depend on the crash type, but also the impact angle. So for a pedestrian hitting a car, the threshold's about 30 kilometres per hour. Same for a motorbike. For cars hitting a tree or a pole, the threshold's generally around 40 kilometres per hour. Side impacts between cars is around 50 kilometres per hour, where head-on collisions, generally the threshold is about 70 kilometres per hour. Fortunately, vehicles are improving, and there are estimates that if drivers were all in safe vehicles, we could achieve about a 40% reduction in fatal crashes. A second video that's been uploaded to Moodle demonstrates how different age Corollas perform in crash tests. And there's a range of different features that are increasingly being incorporated into newer cars to monitor the driver as they're driving, provide improved information, help avoid incidents from occurring, and if a crash does occur, attempt to reduce or mitigate the risk of injury. Finally, we have road factors, and no surprise that these play a vital role in influencing drivers and riders' speed choice and behaviour. And we can influence behaviour with things like the presence of roadside objects, the way we design intersections, the alignments of our roads and the design speeds, and also the road surface condition. Other factors that we can influence as engineers include the road width, number of lanes, roadside activity, if we're installing divided or undivided roads, and the alignment of our roadway, both vertically and horizontally. And in some of the later topics in this unit, we'll talk about how we can go about addressing high priority crash types, which tend to occur at intersections, and how we can also increase separation between our different road user groups to improve their safety. But that really brings us to the end of this presentation, so hopefully now you have an appreciation of the Safe System approach to road safety, which is our guiding strategy for road safety in Australia. You have an understanding of the 4 key areas of speed, vehicles, road users, and roads and roadsides.